We're on a variety of platforms, and these are our public numbers, last updated in March. So fair amount of traffic, fair amount of load, operating on a large global scale. These numbers are supported by a large number of teams with thousands of developers. So how do these developers actually do operations? We follow a paradigm called ops and teams, which is kind of a middle ground between having individual teams, giving them complete team autonomy and letting them do whatever they want with whatever technologies they want. And on the other side, having centralized ops, where you would have just one team taking operational responsibility for all of Spotify. And so how the ops and teams works is that individual teams have operational responsibility for their services, but they do this via a lot of extensive tooling, guidelines, documentation that the infrastructure and operations organization provides for them to make it super easy. The best actualization of this is the golden path, similar to the paved road at Netflix, if you've heard of that. It's end-to-end tooling and very extensive tutorial on how to create a back-end service from scratch, how to run it in production, and how to set up all the ops like metrics, alerting, on-call for it. And so that's how we currently do operations in terms of our current runtime. This is basically what it looks like. Each gray circle represents one host. On the right, you have backend service hosts that are GCE instances running Puppet, Docker, and a Helios agent. And what is Helios? Helios is our own container orchestration system. It's open source, but unfortunately, it was open sourced, publicly announced in June of 2014 at DockerCon, the very same day that Kubernetes was announced. So pretty unfortunate timing there. So how Helios works is that it's a deployment system where we have a Helios master running in each region that talks to the Helios agents and tells it what image to run, what version of that image to run on each host. So right now we're following a single image instance, single service image or instance per host paradigm. And so our new runtime is going to be Kubernetes. So what is Kubernetes? It's a lot of things, but the short recap of it is that it's a container orchestration platform with a very, very massive ecosystem behind it. And it's also, very notably, the only graduated CNCF, Cloud Native Computing Foundation project at the moment. The kind of asterisk to this is that specifically we're running GKE, Google Kubernetes Engine. This talk isn't going to focus on the GKE side of things, more on just the Kubernetes side of things. We did try to, in the very beginning, operate our own clusters kind of from scratch, as in run the etcd backing storage, the master nodes, and the worker nodes all by ourselves. But very quickly it became apparent that we wanted to go with a managed solution. The lesser operational overhead was definitely worth it for us in our case. So in terms of why we wanted to move, that first bullet point kind of covers the generic or the usual answer to this kind of question, in that Kubernetes brings a lot of cloud native magic, autoscaling, right sizing, self-healing, bin packing of containers. But I think it's more interesting to talk about specifically why Spotify, why we want to move to it. So one of the first things is capacity planning. So when I was on the provisioning team, it became very apparent that developers at Spotify both disliked capacity planning and also don't really know how to do it. Capacity planning is it's a difficult operation, and there's a lot of quantitative versus qualitative balance there. What we found that developers were doing were just provisioning up every time they had to actually do capacity planning, both vertically and horizontally. They would just say, I want bigger instances and more of those instances, instead of doing very meticulous capacity planning. So we're kind of hoping to take that completely away from them. It's a form of operations tax that developers didn't want to do, and that we don't really want to have developers doing because they're essentially not doing it right. We also wanted to use less proprietary tech. So as I mentioned, Helios, although it's open source, Spotify is, I would say, the main or only big users of it. So it definitely doesn't make sense for the 5 or 6 developers at Spotify maintaining Helios to try to achieve feature parity with Kubernetes, which is backed by thousands of developers and their open source contributions. Another thing is in this new Kubernetes land, we won't have Puppet running. We've been operating Puppet for some time, and it's become kind of a pain point for a lot of users. And both from the operator and developer side, people are very happy that we're moving away from Puppet. One of the big things is faster experimentation and operations. With Kubernetes, it's a lot easier to spin up and spin down capacity. So things like responding to an incident where you're encountering a big increase in load, either with autoscaling or like without autoscaling, just manually bumping your replicas, it becomes a lot easier. And then for the experimentation side of things, we've already received direct feedback from our users that it's a lot easier to experiment and just like run random things on our testing clusters to kind of experiment with services. Whereas before they had to spin up a series of new GCE hosts, provision them with a proper Puppet role, like run stuff on them, and then spin them down. Now they just have to change some resource manifests and like apply those to our clusters. And so those are the reasons of why we're moving. Now I'm going to cover specifically how we're doing our migration. And so the general goal for our migration is to run all stateless backend services on Kubernetes. That's what we scoped it to. And for this, we've been taking a very iterative approach that has like procedural stages, and each stage is like a very succinct goal. For example, our very first phase was kind of an experimental one, where we sought to run just one service on one cluster and have that service receive production traffic for 1 hour. So a pretty like tightly scoped goal, but it forced us to think about a lot of different things because we were starting from scratch at this point. For example, cluster creation, at this point it was still a manual process because we're dealing with just one cluster and we're only going to be operating that cluster for some period of time. After that, we started to think about a DNS setup. So we had to ensure that all the services, or anything running inside the cluster is able to correctly do DNS lookups for the rest of our internal Spotify network. In a similar vein, the things in the cluster also had to be able to route to, like send traffic to, receive traffic from the rest of the cluster, the rest of the internal Spotify network as well. In terms of ensuring that the service was properly receiving and returning production traffic, we had to do some integration with our existing service discovery. This is something called Nameless. It's in-house built at Spotify. And in a similar vein, we also had to ensure that there was integration with our existing metric system as well to ensure that the service was running correctly in production. And the last bit of that, like operational correctness, was actually logging, ensuring that the service was logging to standard out, standard error, and those were being collected by FluentD and then sent to Stackdriver. So that was fairly successful, and after that, we decided to engage in our next experimental phase, which was to run 3 services on a shared cluster and have those receive production traffic for a few days. So now we're introducing a multi-tenancy, albeit still on a very small scale. But the multi-tenancy forces us to think about a few different things. For example, permissioning by namespace. So for this, we use Kubernetes RBAC, role-based access controls. And this was to prevent developers from one team either accidentally or purposefully disrupting resources in another team's namespace. In a similar vein, we also had to look at resource quotas by namespace. So this is where we start to set limits for CPU and memory for namespaces so that a developer can't either, again, accidentally or purposefully request a ridiculous amount of CPU or memory for their service and then take up all the resources for the cluster and prevent other teams from being able to schedule their workloads. The last thing here was developer documentation. So for this one, up to this point, we were just dealing with one team in one time zone, ours, in New York City. And so it was easy enough to just talk to them on Slack or tap them on the shoulder, send them an email. But now we're dealing with 3 different teams that were across 3 different time zones. So we started to actually write documentation as a way to communicate with our users. And so after the experimental phase, we were basically confident enough, or reasonably confident enough in our ability to, say, run Spotify services on Kubernetes. So then we started to engage in the alpha phase, which was to take volunteer services and run them on multiple shared clusters, one in each region that we were in at the time, GCP region. And so what this entailed was that we initially sent out a survey to all of R&D asking them to volunteer some services that they were interested in running on Kubernetes. And so this had a dual intention. One, that we would inform our customers and stakeholders of what we were actually doing in terms of runtime, like where we were moving to, our plans with Kubernetes, and then also actually getting volunteers and information about those services. And so for those services, they're mostly golden path services, but they have a few minor quirks or differences between them, like for example, co-located memcaches, requiring GCP service account credentials to run, which are essentially secrets. And then we took those services, we communicated with the teams and took those services and basically migrated them for the teams. We would basically work with them to get a working set of resource manifests, submit PRs for their Jenkins pipelines, and get them running on Kubernetes with our assistance. And it's important to note that at this point, we're partially running them on Kubernetes in that their services have capacity on both Helios and Kubernetes. So we don't really need to be operationally sound at this point, because if there's an incident, their first instinct should be to actually spin down the Kubernetes capacity and rely on the Helios capacity that they're used to debugging and troubleshooting with. And so what this drove out for us was a couple of things. First was test clusters. So up to this point, we were dealing with running, say, production traffic for 1 hour or a couple of days, like a fixed amount of time. But now we're essentially running these services in production indefinitely. So we want to isolate those production workloads from the testing workloads. So we created testing clusters, one in each region, just like we had one production cluster in each region. And because these clusters, the majority of their configuration looks very similar to they look very similar to each other. So we decided to script that cluster creation. That was basically just a small Python wrapper around the G-Cloud CLI and some Jinja templating for some Spotify specific stuff like firewalls, networking, DNS, upstream name resolvers, those kinds of things. As I mentioned before, some services require service account credentials, which are secrets. So now we need to integrate with our existing secret system. This is something called CELO. It's been around for very, very long. And we did this through custom resources, which I'll talk about later on in more detail. We also started to look at more initial deployment tooling and CI integration. So for this, we basically just wrote a very small wrapper around kubectl and packaged that up, put it into people's Jenkins boxes, and then ran that wrapper in their builds. And that's all the investigation into deployment that we did at this phase, because we're only dealing with a couple of services. And from these, the variety of services, we got a lot of different learnings in interesting places. I'm not going to go into full technical details here, but some of the interesting things we found were MTU issues with our networking. We found some weird behavior with readiness probes on Kubernetes. We had some syscontrol RMEM max issues with the packet buffer size on cluster nodes, very, very specific things. And then this one I found really interesting because we found out that at the time, kubedns did not support upstream name resolver reverse DNS lookup. So you couldn't do reverse DNS lookup for internal addresses for the rest of the Spotify network from inside your cluster, because kubedns didn't support this. So we opened an issue, and just 2 weeks later, the maintainer of kubedns actually implemented that and closed out our issue for us, which is really, really fast turnaround. We were very, very impressed with that. And so the next part of, or another part of the alpha phase was running 2 high traffic services on these shared clusters. So these high traffic services were fanout and metadata proxy. Fanout you can think of as an internal pub subsystem, and metadata proxy you can think of as the API gateway to all of the Spotify metadata information, so artist and song information. So these are 2 fairly high traffic services. Fanout receives about 1.5 million requests per second, and that works out to about 15K requests per second per instance. And metadata proxy receives about 500K requests per second, and that works out to about 500 requests per second per instance. So fairly high load services. So what this forced us to do was really understand our networking setup on a very granular level because of the low latency that these services required. Additionally, we got to use and experiment with horizontal autoscaling for the first time. This was a perfect use case for it. And most importantly, Running these services on Kubernetes successfully was a great reference example for other teams. Previous to this, we had some other teams had concerns like, can my service run on Kubernetes? You know, it's fairly complex. So what we did was we took the two most complex high traffic services and then ran them on Kubernetes to kind of prove to users that your service can probably run on Kubernetes. So we resolved a lot of doubts there with this effort. So after the alpha phase, this is the phase we're kind of currently in the thick of, we look to do self-service migration. So this is where teams that are interested in migrating to Kubernetes can follow documentation, guidelines like tooling, and either partially or fully migrate their services to Kubernetes. So this phase introduces a couple of things. Now, as operators, we might have stuff running in our clusters that we're unfamiliar with. Previous to this, we were migrating people's services for them. So everything in the cluster we had kind of vetted and were very familiar with. Now we could have something running in the cluster that we haven't seen before. Additionally, the full migration of services entails the need for reliability. These clusters now can't go down because there are services that are only running on Kubernetes clusters and no longer running both on Helios and Kubernetes. And so what this drove out for us was a lot of ops-related things. The reliability, as I said, we need to set up actual on-call for these clusters, alerting. We ran some dirt tests, like disaster recovery tests on the clusters. For that, we used Arc for backups and restores. It's a open source tool by Heptio. Big fans of it, works really, really well. It basically backs up your resources for you in some kind of storage bucket, and you can do periodic backups and easily restore. Arc, Heptio Arc, yep. And then the next part of that, the beta phase, was self-service permissioning, self-service permissioning and quotas for namespaces. So we needed to allow teams to basically create their own namespaces and then have those also set up with the correct RBAC permissioning and sane defaults for quotas, without having to know too much about the Kubernetes side of how to do that. At this point, we also start to look more at sustainable deployment. So the small wrapper around kubectl isn't exactly sustainable anymore when there's hundreds of teams potentially deploying at the same time. The thing that we chose to use for this was Spinnaker. It's an open source deployment orchestration platform, I would say, that's originated at Netflix, but is currently, I would say, jointly mainly maintained by Google and Netflix. And we used it because we wanted to support more complex deployment strategies like canaries, blue-green deployment, manual judgment, and mixing those together. I'll talk more about Spinnaker in detail later on. For this phase, we also needed to make an actual decision on how we were going to store the resource manifests in version control. What we decided for the time being is that all the infrastructure-related resource manifests, things that we as I/O maintain, we have those in a monorepo. And then the actual manifests related to feature services are co-located with those teams' feature services, like the service repos. And so the beta phase, we're in the thick of that right now, but once we're done with that, we're aiming to do the GA phase. So this is the golden path phase, and this is where any new service at Spotify following the golden path is deployed only to Kubernetes and has full integration and support for all of the native Kubernetes benefits and features. And so in this phase, what we're looking to do is vertical autoscaling with right sizing. So right now we have the vertical pod autoscaler running in our clusters, but we have it in recommendation mode only. So it's emitting recommendations about how to size workloads, but there is an actual option to have it automatically change the resource requirements for your workloads for you. But there's a lot of, that's kind of scary actually. So there's a lot of additional work there that needs to be done before we can turn that on. Custom metrics autoscaling is also a feature request that we've had developers ask for already. The default horizontal autoscaling, it works on CPU and memory. And for some people, that's not enough. For example, one team wanted to scale up based on pub sub queue length. So there's additional use cases and other custom metrics that we would need to support for autoscaling. In this phase, we would also have one-click migration tooling. So this would be some CLI tool or some like button in our internal dashboarding that would basically allow you to convert your Helios capacity to Kubernetes capacity automatically. And the reason we'd be able to do this is that a lot of the Golden Path services look very similar, and operationally they act very similarly as well. Here we would also seek to support the everything else in terms of services. So this is like the tail end of services with additional hidden requirements. For example, ITGC services with ITGC requirements, IT general controls. Currently, we're required to track all SSH access to hosts that are under like ITGC. So we need to figure out what this means in Kubernetes. Like, are we tracking kubectl like execs? Do we even allow kubectl execs to those kinds of workloads? Yeah, basically supporting the like tail end of services there. We'd also seek to do migration tracking in this step. So actually having metrics around what is still running on Helios, what is running on Kubernetes, and then trying to shift that number from mostly Helios to mostly Kubernetes and eventually all Kubernetes. And to do this, we are planning to do a migration road team. So this is a strategy that we used during our migration from bare metal to GCP that worked really, really well for us. And so what this was a temporary team of engineers like very familiar with then GCP, now Kubernetes, that would go around to different offices that have developers, hold like lunch and learns, tutorials, and really just sit down with the teams to get them migrated, have that face-to-face time, and that worked really well in terms of getting people to migrate over. So we're definitely seeking to do that again during the GA phase. So that's how we're migrating to Kubernetes. In this process, we've kind of built some custom extensions on top of Kubernetes that I thought were pretty interesting, and they really leverage like mechanisms that Kubernetes provides for you instead of having to like kind of hack around Kubernetes. So I wanted to highlight some of these. I'll explain shortly like what each Kubernetes mechanism is and then how specifically we are like using or planning to use it. So the first one is emission controllers. So these allow you to inject or enforce behavior on like any or all Kubernetes resources. So specifically, we're using it for infrastructure injection and policy enforcement. The first example, the fast forward Java shim container injection, that container is just a sidecar container that is required to add tags to metrics, like Kubernetes specific tags to metrics for your workloads. And so initially, during like the initial phases, we were basically declaratively putting that in everybody's workload manifests. So we had a lot of repetition there. Like everybody's manifest had the exact same fast forward Java shim like container definition. So we thought this was a great way to dry that up and also kind of inject that container for them. This is a big win in terms of updating versions. So when we had it declaratively in the manifests, whenever we shipped a new version of that sidecar container, we would need to send PRs to everybody's manifests to kind of update that image version. But with like the container injection via emission controllers, all they would have to do is we update the emission controller, like what version that it's injecting, and they would need to restart their pods, and it would pick up the new version. The other thing that we're injecting is pod presets into namespaces. So what this is basically an injection point for pods in terms of like envars or specific configuration for containers. So we're injecting envars like Spotify region, Spotify domain that currently services depend on or rely on because that is something that Helios does. So we're seeking to also have that moving forward because people's services wouldn't work without them. And so we were also, declaratively defining that in everybody's manifests. It was a huge amount of repeated code, so we thought that it was a great idea to just inject that instead. The other thing is policy enforcement. These aren't the specific policies that we're enforcing, but they're like canonical, I would say, like policies that other organizations like would want to enforce. For example, like not allowing latest tag for images, basically forcing a declarative image, like a very explicit image. If you're not using autoscaling and you're actually doing like replica, you're actually required to specify the number of replicas, enforcing that all your workloads have greater than one replica for like reliability reasons. So emission controllers for the second one, it's not injecting these, but it will basically not run your workload if it fails these like policies. And so the next thing that we leveraged were the custom resources. So everything in Kubernetes is a resource. Like you think of like an API resource. Custom resources are resources where you define the behavior for it, and you write a controller that kind of works with API server to enforce this behavior. So back to secrets. The problem that we were seeking to solve here was that for Kubernetes, secret resources usually can't be, like Kubernetes has secret resources, but these can't be checked into version control usually because the values are base64 encoded, not encrypted at all. So that's not something that you really want to check into version control. So basically developers were being forced to do like manual, like, create secret, but not check that into version control. It's like a very easy step to forget in your deployment or running of your service. The other thing was that we wanted to have just one source of truth. So that current source of truth is, as I mentioned, like the proprietary system Silo. We don't want to introduce another like source of truth and have developers be forced to sync across those two. So what this basically, if you look at the example of Silo secret, having this Silo secret created, the actual controller backing like the custom resource will basically create a audience insights API2 secret, like secret name that in the who namespace, and like the key value pair will be gcloud credentials JSON, and the actual value will be fetched from Silo. So this actual secret can be checked into version control because there's nothing secret about it really. The actual source of truth is still in Silo. So that was a really easy way for developers to get their secrets for their services. The other thing is resource labels and metadata. So everything in Kubernetes, like all resources, you can add metadata, things like labels, annotations, etc. And it's really easy to work with these from an API perspective. Specifically, this is how we're doing service discovery. So that proprietary system I named before, Nameless. So the Nameless integration with Kubernetes, how it really works is just this like really simple pseudocode where it talks to each cluster and says, give me all your service resources with this nameless.spotify.com/enable true label. And then for each of these services that have that label, register those ports like 80 and 5700 under the metadata name Roswell, like create the SRV record for it, and then now we have a Roswell like SRV record that is returned when other services are doing lookups for Roswell. So yeah, resource labels and metadata are a great way to work with like the Kubernetes API. The last custom point was Spinnaker for deployment, and so as I mentioned before, we wanted to support like more complex deployment strategies, but Spinnaker itself is a little complicated, has its own terminology and kind of its own ecosystem. So we didn't think it was necessary to expose developers to all that, especially when they're familiar with an existing deployment system that we have called Tugboat, also maintained by my team. So those two commands, like Tugboat version create and Tugboat set target version, that's what most developers have in their like Jenkins pipelines to actually create a new version of their service and have that promoted as the current running version. So they're very familiar with Tugboat. They're very familiar with how it works, the concepts behind it. We didn't want to introduce a whole nother ecosystem of terminology to them. So we basically abstracted Spinnaker behind this existing Tugboat system, and we did that via like the CLI that you see, like Tugboat. We added behavior to it to, if there is like a deployment info YAML file in your service repo, pictured below, then it will just simply deploy to the backends listed. So from a developer perspective, they're already using Tugboat, and all they have to do is put that YAML file into their repo, push that commit to master, and then Tugboat will deploy their service to Kubernetes and like the resource manifests that they have in their repo. So it's a very like easy workflow for developers. So those are the custom extension points that we built on top of Kubernetes, and the future problems that we've identified. These are things that are kind of big problems that we know will need to be solved, but not right now. Will need to be solved in the future. The first of those is cluster management. So as I said before, we have automated scripts, but we want to move to a declarative declarative approach. So we looked at Terraform and GCP Deployment Manager for this. However, our current concern, like the reason we're not, just picking it up right now and running with it, is because we rely on a fair amount of really new GKE features as they come out. Basically, as soon as they hit beta, we start to use them. So there's kind of a disjunction between that feature hitting beta and that feature becoming supported in things that are built on top of GKE, for example, like Terraform or GCP Cloud Deployment Manager. And honestly, the biggest thing is the disjunction in terms of the time it takes for that to happen, in that sometimes it could take an hour or a few days, sometimes it could take weeks. So there's a lot of unknowns there that we can't rely on at the moment. And the next problem is MultiCluster Operation. So this is something that we've thought a lot about at the moment. And so as I mentioned before, we are currently running one large cluster per region. And that's fine for the time being because people are running partially on Helios, partly on Kubernetes. But in a world where people are only running on Kubernetes and we still have just one cluster per region, that cluster then becomes a single point of failure for that entire region, which is a reliability disaster, really. So our use case specifically is that we want to have multiple clusters per region, and we don't want to care what exact cluster that this workload should run on, but we just want it to run on at least one cluster in that region. So kind of like a federation layer. So we're following very closely with what the MultiCluster Special Interest Group is doing with Kubernetes Federation v2. I'm not exactly clear on the nitty-gritty details here, but the basic gist was that Federation v1 was very over-scoped when it started. It was basically, we want to support Federation for everything all at once, which is a very complex, very, very complex task. So with Federation v2, what they're trying to do right now is they're working on providing very small building blocks that can eventually support the use cases like the one that I mentioned. So we're following very closely along with that, and we don't have to solve it right now, because as I said, people are running partially, but once people run fully, we're definitely going to need to think more about this and implement something. The last thing is DI and ML cohabitation. So DI stands for data infrastructure. ML is machine learning. So data infrastructure is the organization at Spotify. They're kind of our siblings. They're infrastructure for the data side of things. Unfortunately, it's kind of a pain point in that we implement the same things, similar looking things, but there's not a lot of communication there, and it kind of sucks. So basically, the current scope for the clusters that we're running is just stateless backend services and having simple related workloads like cron jobs for those. But for the future, we really want to support data jobs and machine learning workloads and GPU workloads as well. DI has something open source called Sticks, which is basically running data jobs on Kubernetes clusters, but they maintain a completely separate set of Kubernetes clusters for these data jobs, and they really actually don't want to do that. They want to run on our clusters. So eventually, we're looking to support that as well. So in this process, we have a lot of small learnings and takeaways. I'm going to cover the ones that I feel are the most important. So be mindful and deliberate in dictating terminology. So what I mean by this is when you pick up something like Kubernetes or even Spinnaker, you have to keep in mind that you're really picking up an entire ecosystem with a lot of its own terminology. And often that terminology is overloaded. For example, a deployment and a service as resources. We've had some pretty annoying communication problems there because it's such an overloaded generic term, especially in the tech space. And sometimes people will not know whether you're talking about the abstract conceptualization of a deployment or the actual deployment resource. So what we did here is there's really paying attention to that and little nuances in your communication. For example, always capitalizing the D and S for deployment error services, always italicizing it or using a different font in documentation. Those can actually go a really long way in preventing that confusion with terminology. The next thing was to migrate in stages or a series of goals that increase in scope. So what we mean by this is this really helps you avoid a monolithic migration effort because migrating really large parts of your infrastructure is a pretty daunting task. but doing it in a very like procedural way, like we only want to support these kinds of services, then these kinds, that gradually increase in scope and complexity, really helps you discover and tackle all the unknowns at a very controllable pace. And it definitely is very good for like team and developer morale, because when you're starting out, there are going to be so many unknowns, and if you force the team to think about all those at once, there's going to be like conceptual overload, really. The other thing is the majority of use cases or requirements that we've had, we've definitely felt that a lot of open source tools or extending Kubernetes itself cover them completely. So Spotify has a problem we like to call like not invented yet, not the same thing as like not built yet, but since we've been around so long, a lot of the open source technologies that are really powerful and in use today weren't available at the time at which we needed them. Like Kubernetes is a great example. We built Helios to do a container orchestration, but then Kubernetes was announced and is now a big thing. gRPC, for example, is a thing, and we have our own internal proprietary protocol called Hermes that was invented a long time ago. We want to move away from that as well. So I think the most important message, or I want to like leave y'all with, is to talk to other companies about how they do infrastructure and solve infrastructure problems. So one of my coworkers, Dave Zolotuski, did a keynote about this called Software's Community at QCon Europe about a month ago. And the basic message of it was that we shouldn't think about and solve the same problems independently. We should really just talk to each other, like share ideas and solutions, learn about each other's processes and approaches, like what to avoid, and especially on the infrastructure side of things. And so how we've actually been doing that is that Spotify has joined the CNCF, like Cloud Native Computing Foundation, and we've been doing a lot of talking to like our infrastructure counterparts at different companies, like asking them how they use Kubernetes and Spinnaker, talking about how we use it, talking about issues and approaches that we use. And we've been able to actually avoid some really major pitfalls and like learn about other valuable approaches from these other companies. So yeah, and I hope that we were able to like return the favor to them as well, during these conversations. Just as I hope like in sharing this talk that some of our experiences and learnings resonated with all of y'all. So thanks for listening. If you're interested in working on these kinds of problems for us, or you just want to like work at Spotify, join the band, reach out to me. My email and social media are up there, and I'm always really happy to talk about infrastructure and tech with any of you. So please reach out. Thank you.